Okay, so yeah, I'm gonna talk about the bug that was fixed
Mm.
that we found by chance. Let me share my thing. So yeah, this is quite interesting. So this is the bug. Okay, so I actually did some experiments to try to narrow down the bug as much as possible. Um, Let me show like what my findings. So I took Simon's code, took your code, and I tried to distill it down to its essence. Here's
Okay.
the interesting thing. I couldn't make this simpler. The moment I made this simpler, the bug went away.
Okay.
So this is like the simplest it could get. The key idea, if I change this I double equals 0 to true and false, the bug doesn't happen.
Oh,
Yeah.
okay.
So okay, let's read this. So when I didn't even know it was a bug, I was like, okay, something's fishy is going on, so I reported it here. Um, and then they did some digging and they found out what the problem is. They didn't find the problem because they have tests. Yes, tests is not just things we do in our sessions.
Yeah,
They have
yeah.
tests to make sure the programming language is consistent and doesn't have bugs. But the tests are short. The problem is that when the branches are short, they're inline. I'm not sure if you're familiar with inlining in
Oh,
C++. plus
yeah,
plus.
yeah,
So same thing. There's an inlining in the compiler so that it runs faster.
yeah.
Very short things like inline. When it's
Okay.
inline, the behavior is correct, but when it's not inline, they don't do the ref like the this ref here. They don't do it.
Oh, okay.
Yeah,
Okay.
so they don't do it. That was the bug. That's why we couldn't make this simpler.
Yeah.
Don't, I didn't even think about this. That was crazy.
That's
Yeah.
crazy that you have only two Discord servers.
Oh no, this I have my own personal
Yeah,
Discord
yeah,
server.
I
Yeah,
know
yeah.
that. I
I
know.
mean, yeah.
I.
So yeah, but yeah. So back to identity, right? I'm separating my personal life from what
Yeah.
the initiative I'm doing for now. I'm not sure if I'll change my mind. Yeah.
Is your like real name Marvin though, right? Or
Maybe,
oh,
maybe.
we will not know that. Okay.
You'll never know.
Yeah.
Okay. Um, yeah. So that's the bug. Okay. Yeah. Let's proceed. Yeah. Do you have any questions about this?
Hmm.
Honestly, if you have questions, I may not even be able to answer because it's quite technical.
Yeah, I do not. I will like look at it after the session.
Yeah.
But this guy makes lots of commits every day.
How do you know?
I checked right now.
Oh, okay. Okay. Yeah. Yeah. It's this thing. Okay. Let's go back to Visual Studio Code. All right. So today, oh, let's go over what you did last time first, and then
Oh,
let's
of course,
move
of
to C++.
course.
Oh, you did it.
Yeah, I knew like the modulo greatest
Okay.
common divider. So,
Okay. Interesting. Okay. Wait. Do you answer the first question? The line
yeah.
135. Oh. Oh, okay. I see the answer. It's 136. Okay. Our taken can only return one thing because it works on mutable lists, and splitter only works on normal non-mutable lists. So taken can mutate the one part and return the other, and splitter must return both parts. Yes. So when you're dealing with non-mutation, but you want to return multiple things, you need to create an intermediary structure. So in this case, a tuple that holds
Mhm.
multiple things.
Okay.
So that's why tuples are a very powerful idea in when you're dealing with non-mutation because you get this for free. If you do not have tuples, you must create your own struct, and that's kind of annoying. That's more work, more code, right?
Yeah.
Okay.
I fixed like the merge sort.
Oh,
The
was it broken?
split add didn't return like a tuple. It returned an object that has a prefix and a suffix.
So is the documentation wrong?
Like the documentation is correct about like
Okay.
split add, but it doesn't like return a tuple. It returns like a different object. I don't know what is it.
Okay, I'll investigate this, and again, if it's a problem, I'll report it. Actually, if you want, you can take the initiative to report it.
Okay,
Yeah,
it's
you have the
like
Discord server now.
we can't use the indexes 0 and 1 on this. It it doesn't work.
For split end?
Yeah, yeah. Like we can't change the prefix to the curly
Oh,
braces and zero.
oh,
Yeah,
okay. If you
but
believe
for
it's a bug, you should
but
report
for
it.
any other tuple we can do that. I checked.
Okay. Okay. So sounds like a bug, right? If you wish, you may, yeah, experiment with it. Do what I did. You can, if you go to the
Okay,
Discord server, you see what I did and do that as well. Yeah, you
okay.
can build your reputation in that server.
Oh,
Okay. All right. Let's look at GCD. Create two implementations of GCD and natural for natural numbers. Okay, yeah. So calculate. Oh, okay. Looks like you did the second way, right?
I didn't do the
The
first.
first way.
Okay.
So, okay, I think it's because I didn't really. I only mentioned the natural number template once to you.
Yeah,
Okay,
yeah.
so let me go over what you did first. So GCD natural AB. Yep. Yeah. Standard. Uh, there is another way, which is you first check. You just find which one's bigger and which one's smaller, and then you have a
Mm,
function that assumes the first one's bigger and the first one's smaller, and this will be simplified.
okay.
Because if you think about it, the when you recur, right, the first one is always bigger and the second one's always smaller.
Yeah.
Wait, let me see. Do you do it like that?
No.
Is
Yeah, I added like
okay.
the first else if to do not
Yeah.
worry about that.
Yeah, okay. So you did it differently, but the second way is to always have the A be bigger and have the B be smaller.
Okay.
And you have to do a check at the beginning to find out which is bigger and which is
Mm,
smaller. But yeah, this looks right. GCD modulo. Yeah. Okay. So this is slightly better because you don't have to keep subtracting.
yeah, yeah. It is like way faster, right?
Yeah, because it skips steps. Also, the logic is simpler because notice how there's no concern about which is bigger and which is smaller.
Yeah.
And let's say if A is zero and B is non-zero, you have that test case that it will work regardless.
Yeah.
Okay, so this is a little bit of what I talked about just now. But there's no min or max because the num modulo handles that logic for you.
Yeah.
Okay.
We won't have negatives, right? Because of number modulo.
Hmm. Okay. I'll talk a bit about the structural recursion. So I think I don't know if I'll do this for you. Let me see. Okay. Oh yeah, by the way, for the signature, you can skip line 140, like the signature here,
Okay.
because you already have it on line 142.
Of course, yes.
So yeah, for future reference, you can skip that. So basically, let me go over the natural number template because as we move to C++, this will be important. So
Okay.
when I teach, so for you, right, when I taught recursion, recursive data, I only showed you list.
Yeah.
Typically for other students, I usually go over other examples of recursive data. So another one of those examples is natural numbers. So this is a bit of mathematics, but let me do this at the bottom. Yeah, no, I'll do this here on line 140. A natural number, I just say it's a natural, is one of zero or one plus natural. You see that?
Hmm. Okay.
Now, in some literature, you might see that zero is not a natural number. Okay, for our purposes, zero is a natural number. Okay, for our purposes. Uh, this is a big idea in mathematics, in number theory. If, like people who study numbers, they want to understand, like the same way sorry, not physicians, physicists understand what makes the world, what makes matter. Uh, number theories also want to understand what makes numbers. So let me fact check this. I believe it's called Piano's axioms, but I might
Oh,
be.
interesting.
Yeah, okay. I don't know how it's pronounced. I believe it's a Greek name. I've been calling it Piano's axioms my whole life. Let me put its names. So when you see Piano axioms, you might see some reference to this idea. So Piano's axioms is basically reconstructing mathematics in a very smallest ways. So a natural number is 1 or 0, or 1 plus natural is an example of one of these smallest ways. Another place you will hear this idea is church numerals. So church is a very important computer scientist in the very, very early days of computer science as a field. He is someone that established a lot of what we now do today. He established a lot of the theory. So one of this is idea of church numerals. Um, Remember how I talked about how like we can get very far with function compositions?
Yeah.
So church actually proved that with only functions and function applications, we can do whatever is possible in computing. Okay?
Okay.
So one of these ideas of so we call this is called the lambda calculus. Let me see if I can. I've actually did try to look up the rules of lambda calculus, but no success.
Yeah, I think we did that like sometime before.
Hmm. I think I found it. Okay,
Huh?
I'll introduce this very briefly because it's cool, but it's not actually relevant to what we're doing. Let me share my Google Chrome. Okay, so lambda calculus, literally, you can do two things. You can define a function.
Mm. Okay.
Where's okay, this is not what I want. Where's calling a function? How's this? No, that's also not what I want. Yeah, I tried to look this up just now, but I feel like all these are very complicated. Trying to show you something simple. This is almost it, honestly. I just want to see a function application as well. But yeah, so basically you can create, this is it. You can make one function and you can do
Yeah.
everything. So I'll give you some examples. So here, we can represent true with this. So this is a function that takes in x and produces another function that takes in y and produces x. So the body of this function has another function in it. So we can
Okay.
stack all these functions together. So what this is doing is to encode true, we essentially have a function that takes in two things and produces the first thing. To make false, we have a function that takes in two things and produces the second thing. So
Mm-hmm.
to encode n, what the heck is this guy
Yeah.
doing? Taking A, taking B. Oh, um, so A and B, they will take in true or false, which are themselves functions. Um, so so here we see a function application. It takes in two things. Here we're doing n of true and true. So A and B are true and true. Uh, so A and B are functions, so they're gonna take in all this.
Mm.
Okay, I'm gonna pause here. This is a lot. By the way, I can give this explanation to someone with 30 years of software engineering experience. They're not gonna understand anything. This is very technical. But
Okay.
what I just want to say is that functions are very powerful and you can get very far. In fact, you can get so far, you can do everything with just functions and function applications. Of course, no one writes code like this. No one implements languages like this. This is just theoretical.
Yeah.
Yeah. Okay. Let's get back to Visual Studio Code. Sorry, give me 1 second. Give me 1 second. Okay, I'm back.
Okay.
Okay, so I just talked about lambda calculus, just to talk about functions in church. And we can actually encode natural numbers with just functions.
Mm.
You know,
Okay.
we might do this one day, but I kind of want to get you your competitive programming thing first, just because that's actually relevant to your what you're doing in real life. Uh, but yeah, like this idea of natural is 1 of 0 and 1 plus natural. If we turn that into functions, we have integers, we have the whole of integers in our lambda calculus. But this is just a side fun. This is just a fun tangent. You can just forget everything I just said here. I have a second fun tangent for you. What is a computer? Like if I ask you right now, what is a computer?
What's a computer?
Yeah, what is a
Like a
yeah.
machine that computes things
What does it mean to compute?
to process and give answers.
It's pretty good. It's pretty good. So humans can process and give answers. Is a human a computer?
Yeah,
Okay. That's
of course.
okay. It's a hot take. All
Can
right.
you prove me that humans are not computers?
I can't. I can't. So I guess in some ways
Yeah,
you're correct.
yeah,
Anyway, so this was a big thing in when you're trying to found a new field like computer science, you need to really define things, But so people ask themselves, what is a computer? In the his like computers technically they existed long before computer science was founded as a formal field.
yeah.
Like abacus. Are you familiar with that?
What?
An abacus? Oh,
I don't
okay.
think so.
Let
Okay.
me let me show you a picture of it. I think if I show you a picture, you'll know what it is. Let me share my Google.
Abacus, abacus. Okay, okay. Yeah, yeah.
Abacus. Okay, sorry. Maybe I'm
Abacus.
pronouncing it wrong.
No, no. I didn't know. It's really it's different name in Polish. Like so different. It's spelled.
Oh,
It's liczydło. So
okay. That sounds
yeah,
like vegetable soup.
yeah.
Okay.
But you can call it abac.
Abac.
Abac. Yeah,
I see.
abac.
Okay, I don't know if you had to learn this in school. I had to. I forgot it all.
Yeah, I
But
didn't. I didn't.
yeah, I think yeah, no one dude, no one uses this. Literally no one in the world uses this right now. Okay, maybe someone out there is using it, but like calculators are everywhere, man. Anyway, yeah, this is a form of a calculator.
Yeah.
So is this a computer?
Hmm. I would say it isn't because it doesn't work on like electrical signals,
So
but
you're saying a computer must be electrical
hmm,
signals?
maybe.
See
Uh,
thinking.
hmm.
Ah, no, all of these are electricity. Okay, maybe I shouldn't show
Yeah.
images. Let me, uh, what's his name? What's his name? 1600s computer. Let me see if there's a blueprint of it we can see. Damn.
What does the AI say?
Yo, okay, never mind. So, okay, basically, the idea of a computer actually existed long before, I don't say long before electricity, but like there were mechanical computers with gears and stuff to varying degrees of
Okay.
success. I wish I could show you some pictures of the blueprint. So some people, like, long time ago, I don't know exactly, maybe 1600s, 1700s. Oh, remember when we talk about Booleans, George Boole?
Yeah.
Okay, yeah, so around his time, but I don't even know if I'm pronouncing George Boole correctly. Let's see, let's see what's
Yeah.
his 1800s. So like old, these are old people, okay? Like at
Yeah, I
that,
think like electricity was hmm. Like Nikola Tesla lived in like 1800s, but yeah,
let me see. I mean, this is Wikipedia. Okay, we already have a counter example here, assuming Wikipedia is not lying to us. But yeah, there were attempts at. Oh, wait. Yes, this is the one. This is one I was thinking of. 1800s. Yeah, Leibniz. Like, have you heard the name Leibniz?
not really, not
Okay,
really.
when you learn calculus, you will learn of this name, Leibniz.
Okay.
So yeah, people in the past have already tried like making an abacus, but much faster, and that involved
Mm,
not electricity, but mechanical systems. So are those computers?
Hmm. Maybe.
Okay. So now a computer isn't just what it's made of, right? It's clearly something about what it's doing, right?
Yeah.
Okay. So have you heard of this Turing machine?
Yeah.
So let me see if I can get a good picture. I guess this is okay. So Alan Turing, big guy, he went off to try to define a computer, and this is one of the answers. A computer is essentially a Turing machine, and a Turing machine has very specific rules. This is theoretical computer science. I'm not going to go much into it, but the idea of a Turing machine is that you have a read tape. Maybe this is a better. So a Turing machine isn't a physical device, but you could make it a physical device. First, a Turing machine has a tape of zeros and ones. It has a
Yeah.
thing in the middle that's reading the zeros and ones. It can write to the zeros and ones.
Okay.
And it has a mechanism that determines what to write depending on what it reads.
Okay.
So this is how it looks like physically. If you build it out, this is what it looks like in abstract. So here we have the head where it reads and writes at a specific position. And you have a tape that has all these zeros and ones or whatever. And the tape can move left or right. Um, I think this is examples of rules. For example, write zero, move tape left, write one, move tape left,
Okay.
write one, move tape right. So these are examples of rules. Believe it or not, with this, all possible things that a computer can do, this thing can do
Hmm.
it. It looks very simple, but it can do a lot of things.
Yeah.
Anyway, a big idea of this is the idea of mutation, right? The idea that we are changing something in place,
Hmm.
right? Like
Right.
a tape position can take on a different value. Like 1 second, this thing could be one, another second, this could be zero, right?
Yeah.
Another thing about Turing machines is that they assume infinite space. So this tape is infinitely long, which is why be, a true Turing machine cannot be created in real life.
Yeah.
Because there's just physically not enough atoms in the world, because there's only a finite number of atoms in the world. Yeah.
Yeah.
So yeah, a Turing machine is an abstract model of computer. Let's go back to the Visual Studio Code. I'm gonna share my screen with Visual Studio Code again. Okay, this is a fun tangent. Whatever I say now is just for your benefit. You can forget everything I say. So what is a computer? So an answer is a Turing machine, which is an abstract model
Hmm.
of a computer. Um, and what's interesting is that it is mathematically proven that a Turing machine and lambda calculus are equivalent. Whatever lambda calculus
Hmm.
can do, Turing machine can do it as well, and vice versa. That's very simplistic. There's a lot of math that goes into this. How did they
Okay.
prove it? Honestly, like I didn't even study this formally, so I can't even tell
Okay.
you. But what's the important idea here is that lambda calculus is literally just functions and function applications. A Turing machine is like essentially just mutation. And so you have these two extremes of computation. You have just math, functions and function compositions and function applications. And you have like an actual machine, a logical machine.
Hmm.
And these two
Yeah.
are equivalent. This is called the church. Let me Google the name before I tell you.
Okay.
Church Turing thesis. Church Turing equivalence. Is it church Turing equivalence? Yeah, sorry, this is kind of rough because I didn't actually plan to
Yeah, no problem.
tell you this. Okay, if you want to read, I'm not going to give this a name, but I will say if you want to read more about this, it's Church Turing
Okay.
thesis. So each one had made a thesis and they realized that they're equivalent. Okay, back to back to what I wanted to talk about, which is natural numbers. So if I want to talk about the template of natural numbers, so fun nat temp, and it looks like this. Actually, I don't need the parentheses, right? You see that?
Okay.
And then we can do whatever n is. What's interesting about this is that remember how I said that you only use a template if the thing you're working on is like a data definition?
Yeah.
So this natural number is not a structure, right? It's not a special data representation, it's just a natural number, but we call that temp on it anyway, because that's how we define a natural number.
Mm.
It's a recursive data definition, so we call net temp on it.
Okay.
So you can actually solve GCD using this template. So I'll leave this as a challenge for you. The reason
Yeah.
why I want it, no one does this in practice, but the reason why I want you to do this exercise is to get you familiar with the natural number template and to show you the contrast between structural and generative recursion. So the net template will be structural recursion. Okay. If you
Okay.
do that, what you'll so assuming you did that, here are the observations. So I'm skipping. Oh wait, I forgot the else.
Yeah.
Okay, sorry, let me get back to the bottom. So at the bottom, I'm going to write some observations. What you find is that generative recursion can be more performant. As we can so with structural recursion, you need to check every number between the maximum number. Let's say the maximum number, let's say you're doing modulo of 150. You have to check from
Yeah.
199, 98, 97, 96 all the way to zero.
Yeah.
Whereas generative recursion only does it all in two steps, right?
Yeah.
So generative recursion can be more performant. We see other examples of this. For example, insertion sort and quicksort. Quicksort can be more performant than insertion sort. Insertion sort is the one that uses the structural recursion. I say can because there are cases where that's not true. Depending on how the numbers are presented to you, insertion
Okay.
sort can be more effective. Can you think of a case where insertion sort could be more effective than quicksort?
Mm. Hmm. Like when the list is almost sorted, but uh, they're mm, like smallest part at the end.
Okay. Yeah, the big idea here is when the input list is like very sorted already. But
Yeah.
I
Yeah.
realized something.
Okay.
I think I asked the wrong question. Sorry. Insertion sort, it is true insertion sort can be better than quicksort, but under two conditions. The list is initially very much sorted and the data set is small. But I don't want to talk about data set is small right now because I'm talking in the abstract. So I gave the wrong question.
Okay.
I should have asked, can insertion sort be better than merge sort? Um, but merge sort may do more steps if it's already sorted because of the merge step.
Yeah.
Yeah, so sorry, I should have asked that question instead. But my point stands, right? The idea here is that generative recursion can be
Yeah.
more performant, but it's not necessarily the case. Uh, Regardless, generative recursion is much more complex than structural recursion for reasons stated before. For example, termination is not guaranteed.
Yeah.
When you're making a custom algorithm, you run the risk of someone going into your code and not understanding it and breaking it. Whereas with structural recursion, they're less likely to
Mm,
make a mistake.
yeah.
So these are some things to observe. Um, okay, there are more things to do with generative recursion, but they're more advanced, so I'm going to save them for next time. I think it's time for us to move towards C++.
No
Oh
way.
wait,
Fine.
wait. Sorry. No. Sorry, too soon, too soon. There's actually two more small things before we move to C++. I'm going to create a new file.
course we will.
almost cpp.arr. There are some small things I want to mention before we actually
Almost,
move. Almost,
almost
almost. Sorry,
CPP.
sorry. Sorry. Yeah. Okay, I'm going to close out this Zoom session and send you a new link here, okay? In almost
Of course.
cpp.arr.
Yeah.
Okay.
See you soon.
All right. I'll see you in a minute. Okay, so what I want to talk about is nothing. I'll talk about nothing. Okay, do you see me write nothing?
Yeah.
Okay, I would like you to run it. What do you get?
Nothing.
Nothing. Okay, nothing is a value in pirate.
Uh, okay.
Okay, so
It
I'm going to
it
create a.
doesn't highlight. That is bad thing.
Okay, now if I call get nothing, what happens?
Nothing.
Okay,
Even
so
yeah. Yeah.
pirate, pirate is for beginners and they want to work purely with functions. The thing about functions is that functions must produce a result. The result happens to be nothing. In pirate, nothing is literally a value. In C++, you're not going to return nothing. In C++, you just don't say anything. But here we say
Yeah.
something, we say nothing.
Yeah.
So this is the idea here that if so this is the closest thing in this language to a procedure where it's doing something but it's not producing anything useful. It's not
Okay.
like you can't do anything, nothing. It's just nothing, right?
Yeah.
Yeah.
Right.
Um, I want to talk about I want to go back to loop constructs and I want to talk about this, but this is a new one that we haven't covered for each. I actually need to Google this. I did this just now, but I need to Google it again.
Okay.
I'm going to copy and paste in code. Uh, what's my for each? That's not what I want. I think I found it. Yes. I'm literally pasting this straight from the textbook.
Okay.
Uh, okay, before I show for each, I need to show one other thing before for each is actually useful. So notice how when I do this, if you run it, you get an error, right?
Yeah.
So what happens if we do want to change x to have a different value? First, in this language, you have to do two things. First, you must say var x. You have to mark x as something that's variable. The truth is, every time we use this equal, it's not actually a variable. I've been calling it variables in a mathematical sense, but truly, these are just constants or identifiers.
Mm.
This is actually a variable, var x. It's a
Okay.
variable because it can actually change. If we run now, it's still not going to work. You see that?
Yeah.
Because equals in this language has a special meaning. It means you're declaring something. There's a special operation for changing a variable, and that's calling equals. If we run this, sorry, now it's not going to crash, but if I do this, you will see x equals 2. And if I
Yeah.
put x before and after the tuple calling equals, we'll see 1, 2. You see that?
Yeah.
So we call this reassignment.
Yeah.
Okay. Not to be confused with mutation. This is not mutation, okay?
Yeah.
Why is this not mutation?
Mm. Wait. That's a fairly simple question, but mm.
Okay, so let me change the situation. Let's say we have box
Okay.
of 1 and we change box of 2. Is it, are any boxes changing?
Okay.
No, right? Boxes aren't changing.
Yeah.
Whenever
Yeah.
boxes are changing, that's mutation. When arrows are just moving
Okay.
around but boxes aren't changing, that's reassignment. Okay?
Okay.
So that's
Okay.
the distinction. This is very important.
Yeah. Okay. Okay. So,
Is when we go to C++, when you mark something as const, you are preventing reassignment, but you're not
yeah.
preventing mutation.
Mm. Okay.
We'll talk about this when we move to C++. This is an important idea. So I'm going to comment this out because I'm going to run more things. But yeah, you're welcome to continue to use this as reference. So reassignment and mutation. So with reassignment, we can do something very interesting. I am going to copy code. So, I copied this straight from the textbook. So let me show you how you would normally sum in C++. Uh, so let's say we want to sum from the list 1, 2, 3. I believe that is L capital? L is capital, right? Here it is. Item. So sum, we shall do sum plus item. You add the spaces. Okay. All right.
I think the list is,
Oh, this is, oh, frick, sorry, my bad. Okay, you see that?
yeah,
So this is what you likely see in C++. So I have not shown you each yet, but for each loop, I've shown you for map. So this is in contrast to for map item from list 1, 2, 3.
yeah,
Sorry, I believe the item goes last. You have to do sum from 0 first, and then we do sum plus item. I believe it's
yeah.
this. Shit, it's not.
Mm,
No, sorry. It's brain fart. It's not map. It's not map. It's fold.
yeah, it's
Yeah,
false.
sorry, my bad. Yeah, because some you're mapping the elements. This one you're folding it to a single number. Sorry. Brain fart. Okay, pretend that didn't happen.
Okay.
Um, so you see that they're basically doing the same thing, but what's the key difference here?
Mm, that we are declaring the sum before the loop.
Okay, yeah. What other differences?
Mm, that we are reassigning the sum each time.
Okay, what else?
Hmm.
I think that's it.
Yeah.
Yeah, okay. I just want to see if you get more things. All right. So the first one, normally we say like this, like a very functional approach. You might hear this word. Um, I don't believe this is the best term. I- There is, let me Google this other term before I tell you.
Yeah.
Uh, okay, yeah, I'm just telling you don't normally hear this, but sometimes you may. You might hear applicative.
Okay.
There are nuance between their meanings. But honestly, I usually just say no mutation, just so there's no confusion.
Okay.
Here you'll normally hear the word imperative. Like in English, when we say something's imperative, it's like a command. It's like we're commanding a computer. It's not about getting results, but it's like making a statement, right? So here we,
Okay.
we do things with purely mutations. So there's a contrast here. The first one, things are done with expressions. Expressions are things that have answers. They evaluate to values. Okay?
Okay.
Right. Imperative, we say that they work with statements. If imperative is making a statement, it's like do stuff with no answer. Right. So expressions and statements are like yin and yang. They contrast each other. So there'll be a lot of schools or thoughts that tell you to only stick to one or the other. But the truth is, you're gonna use both. That's just
Okay.
life. It's good to know this difference because in C++, you're mostly going to be relying on statements. Your code will mostly look like the second one and not the first one, but occasionally you might see something like the first one every now and then.
Mm, okay.
I think it's time. It's
No
time
way.
to C++. So we may move back to Pyro in the future, but I want to. So my next
Okay.
goal for you is I want to reintroduce you to C++ with more systematic thinking. And I want you to remember how on our first session, I just watched you solve problems.
Yeah.
We're gonna do that again, but I'm gonna be there to coach you on what techniques, design techniques we've covered that you can use in your C++ code. So that's our next step now.
Okay.
But before we can even do that, we need to set up what compiler do you use for C++?
GCC.
Shit. Okay, I use Clang. Okay.
Oh,
Um,
oh,
okay,
okay.
here's the first thing. How do you normally compile your C++ code?
Like I have like a plugin on VS Code, so
Okay. Oh, really? What's the plugin called?
I think like Code Runner or something.
Can I get it? Like, is that something I can do?
Yeah.
What operating system do you use?
Uh, Windows right now.
Okay. I need to
The fir-
investigate this. For now, you just run your code the normal way. I need to, because you're my first student, I've done C++ with, I've never done this. But I'm probably going to use, to run the code, I'm going to create my own script that I'll use.
Okay.
But you do your way. So my introduction to C++ is
Oh,
oh yeah,
in
yeah, go to
Visual,
intro to CPP.
it's way nicer to look what you are writing in .cpp.
What? You haven't even written anything. What do you mean?
Yeah, but I can see your cursor and your
Oh,
nickname.
oh yeah, I can
Yeah.
see you as well. Oh shit, I did not know that. Okay, all right. Let's start simple. Actually, you know what? Screw it. Let's just do it right. Okay, let's solve some competitive. Let's solve some competitive programming questions. Let's just do it right now. I don't think there's
Okay.
anything else I need to introduce you with. So yeah, what's a problem you faced recently that you want to go over together?
I didn't like, I had a break from competitive
Oh,
programming.
you know what? Remember the first one we did in our first session? Can we go back to that? Can you pull it up?
Of course, yeah, yeah, for
Okay.
sure.
Yeah, we have 10 minutes, but it's okay. Let's just see what we can do. And I'm going to research on how to run the code. But yeah, let's revisit. But I want you to do the actual solution now. Don't do the brute force way. Do it the proper way.
Where was it? It was
And
this,
can
I
you add it
think.
to our Marvin folder as well?
Yeah, yeah, for sure, for
Yeah.
sure.
Oh shit. You know, what, let's go back to Pirate. No, I'm kidding. I'm kidding.
What?
Okay, no. Yeah, let's go. Let's do it.
Okay,
Swappity swap. Okay.
so happy, so yeah.
Oh
I
man,
I did it. I think I did it.
okay. It's
Yeah.
Polish. All right. Wait, is this the correct? Is this like the formal solution or the brute force one?
No, it's the former solution. We use
Okay.
cycles because it was actually uh like a task from uh Polish Olympiad channel on YouTube. So they
Ah,
they taught me how to do it. Yeah, the right way.
okay. Can you delete the solution and start from scratch? But like keep the scaffolding. Like I want you to keep main and like I want you to keep the solve function, but
Uh,
delete the body. And also I would like you to please use English variables so I can understand what's going on.
yeah, of course.
Wait.
So
Keep the pound includes. Like keep the overall scaffolding, keep the structure, but delete the bodies.
what? What?
What do I oh, man, sorry, I keep following your cursor. How do I stop following you?
Hmm. Really?
Yeah,
Uh, I don't know.
okay. All right. Sorry. Yeah, can you create a scaffolding? I guess we're just
You
prepping
you
for our
have
next
like
session.
you have right top. You have pinned me. Yeah, you have pinned
Oh,
me.
is that what it is?
Yeah.
Wow, dude, that was fun. I don't know how you spotted that so quickly. I was still Googling. Okay.
Okay.
All right. Yeah. You know what? Let me see what's happening here.
I can change the names. Okay. So you will.
Yeah, but I do want you to solve this from scratch without relying on a tutorial, and I want
Yeah,
you to apply
yeah.
the techniques we've covered.
But
What
I will do that also.
what is t minus minus doing? It's just t equals one. Okay,
Where?
so I'm just looking at main. It's very curious.
Main.
Yeah,
Oh,
okay.
okay, okay. Uh, I
Uh,
always do that because, like, in some cases use like we check like for multiple tests, right? And so
okay.
I just see in the T,
Ah,
just
okay.
get the input. Yeah.
That's fine. Okay, I found it very interesting. All right. All right, I'm gonna delete all the code except solve signature. Okay. Okay, we have seven
So
minutes. Can you, let's just go through what we can. Do you remember the problem?
I do not.
Oh, okay, you know what? I don't think we're gonna have time then.
Yeah.
We'll save this for next session. Hmm.
Okay.
Let me see. Is there anything else I wanna tell you while we have 7 minutes?
Hmm.
I guess I'll. You're familiar with vector?
Yeah, I think so. Like I can do stuff with it. Okay, but
Do you use it in competitive programming?
yeah, yeah, of course.
Okay, so okay, it's vector. How about okay? When do you use array over vector?
Array of a vector when
Yeah.
like in graphs when you store when you want to store our like neighbors to the nodes, right?
Okay. But why do in theory we could use vectors also, right? Why do you decide to use arrays there?
Mm, like here or
Yeah, like
I
for
don't know.
example,
Yeah.
cows, like line 15 cows max n, we use an array, right? Why not use a vector?
Mm,
Okay,
is
okay, let's go over this.
okay?
Hmm.
Is it faster just
Can be
or
faster.
okay?
Okay, but okay, yeah, let's unpack this. Okay, we'll spend this last 5 minutes just talking. I'll introduce a little bit about arrays.
Okay, of course.
So I'm gonna be an intro of CCP now. So another reason why I don't really like C++ for teaching is because I have to write the boilerplate. But anyway, so I want to talk about arrays. So let's do int of nums.
Yeah,
Okay, what is this doing?
like reserving space, right,
Yeah,
for 1,000 integers, right? Each is like 4 bytes, I suppose.
okay. Yeah, I mean, depend on what platform we're running on, but yeah, let's just say four
Yeah,
bytes. Okay, it's an int. It doesn't really matter, okay? Okay,
yeah.
here are some properties about when you use arrays, right? They're contiguous in memory.
Oh, right. Yeah. So why I
So,
didn't follow that? Yeah,
um, so this is huge, by the way.
yeah.
The idea of
Not,
memory, this is a whole different topic. Whole different topic. Um, I don't want to really introduce you to it yet. I think you get an intuitive understanding of it, and that's good enough. But just know that because it's contiguous in memory, it's very good for the computer.
yeah.
Good for CPU.
Not like in Python, right?
Depends. If you import certain
Like,
libraries,
yeah,
you can
yeah.
actually get contiguous arrays.
Without
Yeah.
NumPy, without NumPy, right?
Yeah. Yeah.
Yeah,
If you're using just a regular list, chances are it's not contiguous in memory. But again, there are different strategies. Okay. We're getting ahead of ourselves. Another property is that fixed sized. No matter what, you have 1,000.
yeah, yeah.
But
Okay,
here's the thing.
okay.
What you can do is you are allowed to just use as you want,
Yeah, and we can
as many
leave
as you want,
else
as long as
empty,
it doesn't
right?
go over
Yeah.
1,000, right? For example, let's say you only need 100. You use the first 100. That's okay.
Right.
So for things like Python, Python lists, our pirate list, you can get more, right? It's arbitrarily large.
Yeah.
There are different implementation strategies. For example, in like Java's array list, what it does is it literally if you want a bigger list, what it does is it takes your old list, it's going to request a bigger array, and it's going to move all the numbers on your old array and move it to the new array. That's what it does.
Okay.
So one strategy of getting a bigger array is to ask for a bigger array and move it all over. So you can maintain contiguous memory. It's still fixed size, but the problem is there's a cost to moving, right?
Yeah.
So there is a cost. It's not for free. Another strategy is to have a linked list of arrays, essentially a linked list of arrays, right? You ask for 1,000. Oh, let's get another 1,000. How do you refer them to each other? You just have a pointer. Like what we did with our REST, our linked list in the Pirate. We can do that with arrays as well. Problem with this,
Okay.
we lose contiguous memory, but we don't pay a huge cost for asking for a bigger array, right?
Yeah.
Yeah. Um, this num, if I write nums here, what type is nums?
Nums
Yeah. What type
like
is nums?
int, right?
Just int?
Is it like it's uh pointer, right?
Yes.
I
So,
didn't know how to say the words in
okay.
English. Sorry.
Oh no, all good. Okay, pointer, yeah. Okay, do you put a
Pointer.
star next to int or x? Where would you put it?
It doesn't really matter, right?
But for you, in your code, where would you put it?
Like next to int.
Okay, okay. So, uh, as long you just keep it consistent. So for you, I usually put it next to x, but for you, I'll put it next
Okay.
to int.
Okay.
Uh, so in software engineering, it's very important to stick to conventions in the code base. So if people do it one way, you just follow other people. Otherwise, you're just messing things up, right?
Okay.
But here's very important. What's the type of y?
Uh, like also, hmm,
Is it
also
int
a
star?
pointer.
It's not. It's int.
It's not.
Because in C,
Oh,
like you
okay.
can put the star anywhere, but as what the compiler actually sees is actually star x. What you're saying is, uh, the pointer to the pointer to x is actually an integer. That's what it's actually saying. If you were
Huh.
to reference x, you'll get an integer. If you wanted to say y is pointer in, you have to do like I believe it's this. I could be wrong. Anyway, just keep this in mind. What I'm trying to say is, don't do that. Just on one line, declare one thing. Don't try to do anything special. It's
Okay.
like in
Okay.
competitive programming, people sometimes do things like this, right?
Yeah.
When you put your star next to int, you will get problems. So I advise you to don't actually do this. I advise you to do this. At best, you do this.
Okay.
Even if you
Makes
wanted to
sense.
do this, no, do not do that with pointers.
Okay.
So okay, I'll write this down for your benefit so that you remember. Warning, right? Okay, let's pause here. I do want to go over more mechanics of C++ in the future, but I also want to see you problem solve using the techniques that we have seen. Okay,
Okay.
all right. I hope you learned something new today, and I'll see you tomorrow.
Yes, see you tomorrow.
All right, see you tomorrow.
I will mail use like today also with the
Sorry, what?
handle. I will like mail you with the handle, right?
Mail me the 100?
The handle, like the
Oh,
name.
yeah, yeah. Okay, yeah, yeah, yeah.
The
No problem.
handle. I how to say that?
Handle?
Handle. Okay.
Yeah, yeah,
Okay.
yeah. Okay. All right, sounds good. All right, I'll see you
Yeah.
tomorrow. Bye bye now.
See you tomorrow. Bye.